Hello, and welcome to tutorial number 26 of the series of 2020, where we're going to look into curved folding of steel sheets and how to do that in Grasshopper. Last tutorial number 25, we looked into origami, and I was thinking that, well, origami is most of the time just has this kind of a straight line fold, but what if you use a curved fold? And then I started looking into these really cool, I guess more experimental pieces, and figured out that you can indeed make a curved fold, and we'll be trying to do that. So let me just find one that's kind of, yeah, something like this. You have something flat packed, then you just have these kind of seams, these kind of ridges, which you fold, and you end up with a three-dimensional shape right here. And some of them are quite cool, some of them are quite boring, but this is pretty damn cool, I think. So let's do that in Grasshopper. And before we begin, there's one thing. Most of the steps that I take here are going to be quite similar to the ones that I've already done in my previous tutorial number 25. So I will be going through them quite fast. If you want a slower version, just check out that tutorial. I'll probably put a link in this video description for you to check out. Okay, so let's begin. I will start by specifying 0. Hello? What's up with that? I'll start by specifying a size of my sheet, right? Of my steel sheet. And I'll just draw a rectangle for that. So I just have this kind of rectangular curve. That's my steel sheet. And then on it, I will draw, I guess, curves, right? So I will just take my control polygon curve, or what, control point curve, sorry, and I will just draw, let me just get that perpendicular snap turned on, and maybe smart track. Usually I don't use smart track, but in this case it might be useful. Smart track. There we go. So I just draw out a curve, and it doesn't need to fit perfectly. Let me just do this, for instance. It doesn't need to be perfect. It just needs to be there. And I'll see that this curve, where it intersects with the rectangle, is going to be a fold line right here, right? So I want actually to have two of them. So let me just, I'm lazy, so I'll just mirror the one that I already drew to the other side. And perhaps we'll have a third fold line, which is going to be boring, and it's just going to be a straight line segment. Later on we can kind of mess around with that a bit more, but for now I'll just leave it as a straight line segment. Alright, so we drew a basketball court. Who cares? Okay, so I will, and that's all I need, right? Perhaps I should create, just to make it pedagogical, I will create two layers and call one of them mountains and the other one valleys. And mountains will be blue and valleys will be red. And I will take these two arcs and I'll say that those are mountains, and I'll take the middle line here, and that is a valley. So mountains and valleys, right? Valley means that as a sheet of paper folds, let's say we're looking at it from a section of it. If there is a valley line right in the middle, just like here, so as the sheet of paper folds, it will fold like that, right? If there is a mountain line here, right, running through the surface, it will fold upwards, right? So it's just basically the direction of the fold, nothing more. Okay, let's begin working with it in Grasshopper. I already have like a small setup here, but I will be repeating everything. This is just my notes, so don't worry about that. I will reference in my my rectangle here as a curve. Set one curve like that, and I will make it into a surface. Since it's flat rectangular curve, I can just type in surface and just plug in my curve into a surface, and it's going to make a surface. Okay, that's good. And then I want to take the surface that I have and I want to divide it into into 4 surfaces with these 3 curves, right? All of these 3 curves. So I will say surface split, and I'll connect my surface to the surface input. And for my splitting curves, I will just type in CRV again, curve component. Right click on it, set multiple curves, and I will just set all these 3 like so. So now, hard to see, let me hide the curves for a bit, layers of the curves. So now you can see I end up with 4 surfaces, which is great. Then I want to divide them up. I basically want to have more resolution, right? So I want to divide them up into small, these kind of stripes. I can do that by using a tool that's called ISO trim. And it asks me for a surface input, and I have 4 of them. That's perfect. And then it asks me for a domain. And I'll stop. There's a problem. It asks me for a surface input here, base surface, and I'm giving it trimmed surfaces. So ISO trim will not work because, for instance, if I have a surface like this, right, and I trim it with, let's say, this shape, trim like that. If I trim it, this is a trimmed surface, right? Looks okay, but if I were to say points on, you can see that the control points are from the original surface, meaning that the domain is also going to be from the original surface for each one of these. Like every single one of these 4 pieces will have the same domain, and it will not work. So we can't do it this way, but instead we need to do it in between the surface here and the surface split here. So let me actually group that part. So the surface, the large surface, will need to be divided and then split with those 3 curves, right? Like that. Then it will work. So now let's divide up the large surface that we have here. So ISO trim asks us for a domain, and I can get a domain by just going to math, domain, divide domain squared, 2-dimensional domain. It asks me for 3 inputs. The first one is my surface. The second 2 are going to be how many divisions. So I don't want any divisions along, I don't want any divisions in the same direction as I have my fold lines. I want divisions in the opposite direction. So one of these inputs is going to be 1. And the other one is going to be, let's say 11, I don't know. And I'm not sure, I'm just, plugging them in 1 and 11, but it might be other way around for you. You will see it once you connect your surface divide to the domain, your divide domain to the domain input here. Like that. Let me hide a bunch of stuff. And I can see that I messed up, you know, the divisions are indeed going in the same direction as the fold line, so I need to change these two guys up. Come on, go away. Like that and like that. And now it's exactly as I want it to be. Increase, decrease. Don't do too much though. I will do, for now I will do 20 and then we'll see. We will see if it works with 20. Okay, so we have that going on. And we have our fragments, right? So every one, basically the way it works is we have a surface, then we make 20 surfaces, you know, 20 long surfaces with this component. And then we take every single one of these long surfaces and we split it with 3 curves, right? So 20, we should have 80 surfaces in total, and we do. Okay. So now I need to make them into a mesh, and it's going to be quite easy. I just need to divide, no, not divide, sorry. I just need to get the corner points of these surfaces, and I believe discontinuities will give me that. Yes, indeed they do. So I get my discontinuities here, 4 corner points. And then I will just simply use, I know for a fact that all of these will have 4 corner points. Every surface here will have 4 corner points. So that means I can use construct mesh. And the way construct mesh works, it asks you for points, and then it, according to, see how this already has a default value of quad between 0.0, 0.1, 0.2, and 0.3, basically make a quad. It's just going to make a single mesh face between the those 4 points that you give it. Perfect. We do it. There we go. And I just keep hiding stuff. So now construct mesh gives us 80 mesh faces, right? All of them in separate data branches, so I don't need that. I will flatten it. So now everything is in a single list, and I will just use combine and clean from Kangaroo 2. It basically just joins up the mesh and cleans it up. Okay, so we have a mesh ready. This whole part is responsible for making a mesh. Let me just check. Yes, we are well on our way. Now I will not be doing those 2 parts. I will be doing them a bit later. I just want to see this folding in action. So we have a mesh here. Let me position it properly. We have a mesh here. I will just create a mesh component, just like that. Okay. And now I want to create a Kangaroo script, right? So I will go for a solver. Again, I know I'm rushing, but the slower version is available on tutorial number 25, so you can check it out. So toggle is false, button is a reset button, and then I entwine to be able to get more than one input in. Then show will be always at 0, 0, and we will be showing a mesh. And actually I just want to create a separate mesh container here for the show, just like that, and connect these 2 guys. Perfect. And then solver output will also come out as a data tree, so I exploded that data tree, and I know that since mesh comes into 0, 0, from 0, 0, a mesh will come out. And I'll just make a custom preview, make it pink. All right, and I just hide everything. So now we have first goal, and we have a solver, you know, doing its thing. Now for our other goals. First of all, we don't want the material, you know, this sheet of metal or sheet of paper, doesn't matter. We don't want it to be stretchy, right? So I will go for goals mesh, edge lengths, and it asks me to give it a mesh. Sorry, I'm just thinking. Yeah, so I will give it a mesh here. Yeah, and I will say the length factor is 1, that's perfect, and strength, I will just give it like 1,000 strength. So definitely a really, really strong force. Maybe 1,000 is a bit too much. Let's try 100. How much did I use here? I can't see. Come on, just let me unfreeze this. No, that's the wrong one. 100, yeah. So I will use 100. Okay. So now it's basically keep your every line on the mesh tries to stay as it is and also show the mesh. We have 2 goals. Nothing fancy. Okay. Next up, we need bending, and for bending, we will be using goals mesh hinge. Right? Oops. Hinge. This goal right here, which connects to 0, 1, like that. And then it asks me for 4 points. So I'll just go for, I could extract them manually, but I am lazy. So I'll just go to under kangaroo 2, mesh hinge points. Hinge points right here, and just connect them like so. So it's like door hinges, right? And I'll connect mesh to here. Okay. So we have that working. And the strength, we don't care. The rest angle, though, we do care. So the rest angle is going to be, first of all, it's going to be in radians. So I'll convert, I will be using degrees, but I will be converting them to radians here. And degrees are going to be between 0 and 120. For now, let's do 120. Connect them like so, and that's my main thing here. There we go. Okay, so the problem now is that every single edge here is a hinge, right, for this definition. So everything will kind of crumple. We only want edges that are running right along this curve and this curve to be hinges. And again, I did that in tutorial number 25, so you can check out the slow version there, but I will be, of course, doing it again here. But much faster. Line, I just kind of create a line between first point and second point to show where the hinges are. And yes, it triangulates the mesh, don't worry about that part, as long as we still get these lines here, and also we will fix the mesh triangulation in a bit. So we get all of our hinges, and then I will create a curve component, set multiple curves, and I will just reference in these 2 arcs here, just like that. And I will say every line here should give me a center point for each line here. Evaluate length / 0.5, and just connect it like so. So I get a oh yeah, okay, yeah, that's perfect. Is it though? Why are you not, and you as well? What's up with that? Wait, something's fishy. Hide. Are you considered to be a naked point? And V, something's messing up. Just a second. Panel, no, not panel, just point. Yeah, so this point is a naked point for some reason, but that's fine. We can fix it by right after combine and clean, we can use align mesh vertices, align vertices, or yeah, let's try align vertices. And the result has 107 vertices, and this one has 107. Okay, 0.1. Why are you not working? This align vertices component never works. God damn it. Okay, let's see. Weld, mesh weld vertices. This component right here. What about you? 105, super. Okay, so this just works. I don't know. I'm having problems with the align mesh vertices. But basically, this one just add to group. This one just removes all of the duplicate vertices from the list. So now all of the midpoints are correct. Okay, good. And basically, I just want to measure. I just want to drag these midpoints towards the curve, right? So I will pull point. So pull every point towards the curve, and I get a bunch of distances. And according to the distances, right? So basically, it's just measuring. It's finding the closer curve from these two for every one of these points, and it's just measuring distance to them, right? And from these distances, I will ask, is it smaller than, I don't know, like 0.1? We need to work with tolerances for this to work. So is it smaller than 0.1? If it's smaller than 0.1, it's fair to say that it's probably on the, it's the correct, it's a point that is on this curve. Okay. And I have true and false statements, and I can cull pattern with these true and false statements. And for now, I will just cull the lines just to see if it works or not. Control A, hide, and hide stuff here. Yeah, seems to be working. So I cull all the lines. But the thing is that we don't want to cull the lines. What we want to do is we want to cull the hinges, right? We want to cull the holes, so that the goals, so that it only bends on these lines. So I will cull, instead of culling lines, I will cull the hinges and connect that to my entwine instead of the original hinge. Okay. And I will just group this part. So we have our mountain folds here, and I can just call this mountain fold. Okay. Shall we see how it works? It should work at this point. I will just hit reset, hit run, kind of find a nice angle to look at it, and start increasing the degree. Oh, yikes. Start increasing the degrees. I mean, it is folding. Don't get me wrong, it is folding, but it could be better. It definitely could be better. Okay, so let me change it up, and let's do the valley fold, this straight line here. So I will just copy paste this, connect it as well, and here as a curve, where's my valleys curve? I will use this one as the curve input, set one curve, and instead of mountain fold, I will call this valley fold. Okay. And now the valley fold will need to have a, like it folds other way, right? So it needs to have a negative rest angle. So I'll just type in negative, connect radians to the negative x, and connect negative like output to the rest angle, like so. All right, so might as well check out how it looks like now. I will reset, run it, start folding it, and it just destroys itself. I mean, it is folding, but it's not great at all. Okay, let's make it better. So, and that's why we have these two more like clusters of things here, and also like some stuff in the back, but it's mostly those two clusters. So between the mesh that we get here and the mesh that we feed into our simulation, stuff needs to happen, right? So that stuff is going to be me manually triangulating the mesh. And I don't remember how I did that. That is not how I did that. That is how I did that, okay. So me manually triangulating mesh first. I will say, well, let me disconnect it so that it's not in the way. Like that. And I'll say, give me, for every polygon, give me a polyline, like surrounding that polygon. So Weaverbird's, where is it? Weaverbird, extract, face polylines. This bad boy right here. Okay, and now give me this continuities. Give me the corner points of each of these polylines. So I get these kind of 4 corner points again. And then give me polygon center as well. Right, so it gives me, well, it gives me 3 outputs, but it's basically 3 ways of how to calculate the polygon center. I always use the first output here. So I can just kind of type in point and just say I will be using that one. Okay, so we have points coming out here, and we have points coming out here. And I want to basically create a data tree where I will have 4 + 1, 5 points in every separate list or branch of a data tree. So I will be using merge for that, and I'll be connecting my points into merge input D1, my corner points, and my center points into D2. And as you can see from the fact that one of the lines is dashed and the other one is not, it means that this is a single list of center points, while this is a separated, it's already separated list. So what I'm going to do is I will graft this single list of points. So now every center point gets its own branch, and hopefully it's going to merge properly. And apparently it does, because now when I hover my mouse over the merge output, I can see it's 5 points or 5 elements in each data branch. So I can do, so then I just need to kind of use this and create a mesh between those 5 points. And the way we do it is, this is not a good way, by no means, but it works, so we don't care, right? We use Delaunay mesh. We use this tool right here, right? Which asks us for points, and I just give it points, and it just basically creates a mesh through those 5 points. So now we end up with 80 meshes again, which all of them are in separate branches. So first of all, let me flatten it out, just like that. And then I will again use combine and clean. And I will again use the weld vertices component. I'll just copy and paste it in like so, just in case, just to clean it up. So this whole part here is basically us constructing a mesh, like getting a center point in each previous polygon and constructing 4, how do I explain it? We have a polygon, we get its center point, and we construct one, let's just do it this way. We construct 4 triangles, like triangular polygons on it. So we basically just increase the polygon count by 4 of our mesh. And thus, if we connect it now to the mesh input here, it should be much nicer. Let's see. Custom preview, reset. Looks like that. Turn it on. Start increasing the degrees. It's still a bit messy. But now at least the center seems to be working quite well. So at least that. Okay, so we have that going on. Now last thing before we kind of finish up and just make it pretty is going to be creating cross bracing. You would think that we are creating cross bracing by doing what I just did, but we are not, because you do have that center point. I actually want to have an X, like these 2 lines making an X on each of these polygons, and not letting the polygons swivel and twist and turn. And tutorial number 25 explains it. You know, the reason behind all of the reasons behind it. All right, so I'll be reusing the polylines, face polylines tool here, and I will be just getting the discontinuities again from it. So I get the 4 corner points, right? And then I will use list item, and I will just extract the first item of the list, the second, the third, and the fourth, right? So 4 corner points extracted separately. And I will draw a line between the first corner point and the third one, so one part of the X, and I will draw another line between the second and the fourth corner point. So we have a bunch of X shapes here. And I will merge these lines into a single happy family and flatten them out. So now all of them are in a single list. And for these lines, I will do a separate thing. I will say mesh, no, not mesh, line length. Let's go to kangaroo 2, goals line, length line, and I will say that these lines with the same, perhaps show should be here a bit higher. These lines that I have here, these cross braces, should also try and keep their original length. If none provided, starting length will be used. Perfect. So they should keep their original length with the same strength as any other edge of the mesh, like that. So that's an additional goal that we give our mesh to make it stiffer. And now if I run it through, let me hide that. Now if I run it, it should still kind of mess up a bit, but much, much less. There we go. See how much cross bracing matters? So we end up with something like this. Cool, huh? So now you can start messing around, you know, with the patterns that you have and so on that rectangle, because all of the inputs, show selected, all of the inputs that we are using is, you know, these curves here. So you can start designing with this tool and start kind of seeing what works and what doesn't. And keep in mind, some things just you cannot bend, right? It will break. So there are rules behind what you can bend with a curved line and what you can't. Before we finish up, there's one last thing I want to do, and it's color it according to how much the material stretches. So every material has a certain amount of flexibility in it, and I just want to color it according to how much I want to color the mesh according to how much each polygon kind of stretches out. And I can do that by measuring the area. So I have this kind of simulated mesh here, and I have the original mesh that is here, right? The flat one, before simulation. So before and after simulation. So I will just create a mesh component and connect it like so, because I don't want long wires. And I'll just drag it out, and I will right click on the input, mesh input, and choose to go to wire display and choose hidden. Usually I never do this, but in this case, sure. And I'll just rename this mesh pre-simulation. There we go, mesh pre-simulation. And this is mesh post-simulation, right? So we have mesh pre-simulation and mesh post-simulation, and we need to see how much every polygon stretches. So what I'm going to do is I will say, give me an area. No, maybe we need to get faces. Mesh faces. Hello. Fine. Let's just get Viewerbird. Where is it? Where are you? Viewerbird. Face polylines again. Face polylines for this mesh, and face polylines for this mesh. So we have polylines, and I will just measure the area of these polylines here and area of these polylines here. And I will compare the change between the original area for every polygon and the new area, right? So I will subtract from the original the new area and see what kind of output I get. And it's, you know, these are the changes in square millimeters or whatever between the original and the new for each polygon. And some of them are in minus, some of them are in plus. I don't really care if it's plus or minus, you know, if it's a negative or a positive one. So I will go to mesh. No, it's not going to be mesh. It's going to be math operations absolute. So everything is a plus now, right? A positive value. Okay, so we have a bunch of positive values, and then I want to have a percentage, you know, how much is this value from the original area in percent? How much did the original area change in percent? So I will divide this original value by this change value, how much it changed. I will divide it by the original area, and I will get a percentage, right? No, I will not. I need to multiply it. Multiply by 100. Proportion, you know, you need to multiply it by 100 to get percentage. And this is percent, how much it's changed. So we can see that some of them are even changed 20%, which is a lot, but you can control it by increasing this value right here and forcing it to kind of be even more rigid. And let me stop the simulation for a bit. Okay. So we have changes here. All right. And now I want to color this whole thing, right? So I will color it, and the way we color it is by, how do we do it? Can we just mesh explode? I'll just explode the mesh, and I will say give me, sorry, I'm just thinking a bit. I have this mesh exploded, so this is every face and this is every value for every face. So we need to somehow convey these values into colors, so we will use gradient. We need to use gradient, and I will say that low values are something calm, something blue, and high values are red. And I consider low value to be 0%, and I consider high value to be if you have 1 square centimeter, sorry, I'm just, wait, just give me a second. If you have 1 square centimeter and stretches out by 10%, let's go for 25%. That's a really high value for stretching. Okay, and you know, the actual parameters are the percentage that we got from here. So now these are converted to, the percentage is converted to colors. Okay, and can I color mesh? Can I use mesh color? I saw something. Mesh colors. Okay, I will try to use mesh colors. Doesn't work. Let's try grafting and grafting. Ah, there we go. Now it works. Okay, that's perfect. So the mesh is colored, and I will just join the mesh up. Yeah, I need to flatten this, so I'll just use mesh join to join it up, and that is our final mesh right here. Let me bake it, default, okay. I just want to see, oops, not artistic, no, oh, shaded. Shaded view, yep. So these guys right here, this is where most stress happens, and I think there's, you know, that's because of this arc right here. It's very, you know, very heavy, and also on both sides these two arcs are stretching it out quite a bit, so it's doing that. Arctic view. Yeah, works in Arctic view as well. Super. Kinda. Ray traced. Doesn't work in ray traced. Anyway, so that is all from me. As always, the files are going to be in the video description, so you can just download them and play around with them. Hope you all enjoyed this one, and I will see you on Wednesday with some more cool stuff. Bye!